this recording. And what we'll do today is to go over the practice final exam so that you guys know what will be in the final exam, what kind of question, and we'll go from there. And I made a grading mistake in the first question of the exam, so I'll be regrading that one. I think it can only bump up the score of people, so you might see your grade going up a little bit because of that.
Or down. I said or down.
Or now.
It never works out for me.
All right. So I think some of you probably received the email from me from last night, about the practice final exam is already online. So that's what we'll do today. If you had a chance to take a look, that's great, because it gives you a little bit of time, just to work out the problems, by yourself, or try to work out the problems first. If not, that's okay. We'll just go over it today, right now, and we'll take a look at those questions. The practice exam is in the form of a tar file. So after you download it, you have to unpack it and do something with that. I'm going to remove the folder from yesterday. This is from cisp310, and we'll do the one from today.
Hey, Professor, is the finals gonna be more like the midterm?
Yes.
Or like your previous semesters we have multiple choices.
Nope, no multiple choices.
All right.
Yep, makes it a little bit harder for me to grade. Scantron. All right, so there are 3 questions that I have prepared. Okay, this one is the first one. Okay, this one is basically kind of based on find max n, but it's called sum n. Okay, so for summation. I did not even bother to rename the label so that people cannot just look at the label and kind of use that as a clue to figure out what is what. Okay, so that makes it a little bit easier. The instruction for this particular question is to write the subroutine in C. So I want you to decompile the assembly code back into C code. And the limitation is you can only use structured code in C and C++, which means you cannot use go to, break, or continue statements because those are considered not structured. Okay? Because that's what we're trying to do. All right, so when you're given a problem like this, what are you going to do first? I will not start to write a single line of code until I have analyzed the assembly code, at least to the point that I think I know what's going on. Because with any type of C subroutine, you have to fill in a few things. One is what is the return value, what is the return type. One is so you got the return type, you have the parameters. Okay, so you have to figure out what are the parameters that we're dealing with here, and also the logic of the subroutine. What is the code inside the subroutine? So all of those are important, and which way you work on first, is entirely up to you. So what we want to do is to just kind of go through this code, and I'll just kind of add comments as we go through this. Okay, so I would say this is standard entry code to push EBP, to save EBP. And what I'll do is I'm just going to look for the exit code, popping EBP. So just to make sure that they're here. So standard exit code, nothing special here. And this particular program is not designed to be tricky. It's really kind of more or less a straight translation. This one is the same thing, ditto. Standard entry code, because we always copy the ESP to EBP to basically make my own frame pointer for this particular invocation. And it should have a matching, but reversed, opposite, instruction at the end. So this is also a part of the standard exit code. So nothing too special here, okay? Standard C subroutine issue, saving and restoring the EBP at the beginning, saving at the beginning and restoring at the end. Okay. Okay, this one here is to reserve space for my local variable. So what you want to do is to say, okay, what am I adding to ESP? And the definition of last local var is sum. What is sum? Sum is PTR minus 4. What is PTR? PTR is old EBP minus 4, and old EBP is 0. So we're dealing with effectively -8 here. So we'll say, reserve 8 bytes for local variables. So all of this stuff here, the entry code, pushing EBP, move ESP to EBP, and also changing the stack pointer, moving it down a little bit to reserve space for local variables. That's all pretty standard stuff, okay? Almost every subroutine have these instructions. Save for the one that we are on right now on line 18, because if you do not have any local variables, there's no need to reserve any space on the stack. Yes?
So, are you going to give us that as the old EPP equals 0, the first part? Will you give us
Yeah,
that?
yeah,
The beginning part?
yeah.
Okay.
That's usually how I write my subroutines. I don't, try to memorize the offsets to parameters and local variables. So I think it's okay, to include all that stuff, All right, so what this instruction is doing is moving a $0, which is an immediate operand, into sum in parentheses EBP. The first operand is called immediate, and the second operand is called the base addressing mode. So at this time, I think we should kind of be familiar with these different addressing modes already, because it's basically the foundation of of this class. So this one, we'll just say, okay, sum gets 0. Are there any questions about line 20? Line 20 is basically one line of assembly language code to one line of C code. That one is actually a pretty easy one. And that's outside of any control structure. So this is actually literally the first instruction or the first statement in the C program. Okay. The next few lines, let's figure out what it is doing. Okay. So what you want to do is to keep track of the registers. If you see a few instructions, they all involve the use of the same register. You kind of want to keep track of what it is doing. Okay, so in this case, EAX is just EBP. Now, right now, what is EAX? How would you describe EAX after the instruction on line 22? It's EBP plus the displacement or the offset from where EBP points to n. Okay, so what is the other way to say that? It's the address of n. That's how we get to the address of either a parameter or a local variable. Is that making sense? Okay. Because if you want to draw this as a picture, okay, so let's say this is a call frame. So if this is a call frame, we have a whole bunch of parameters here. We have the return address here. We have the saved EBP here, and then we have some local variables here. So that's a typical picture of a call frame. EBP itself as a register points to its own old value, EBP. And the way I define the labels, n, PTR, sum, and last local var, they are basically displacements or offsets from where EBP points to the individual things that I want to access. So in this case, n is my parameter, and so this much distance is my label n. So by adding n to EBP in the temporary register EAX, EAX becomes the address of parameter n. Okay? Are there any questions about this part? Because this is actually quite important. We are not using any instructions or addressing modes that we haven't seen before, but we're using all of those in order to calculate the address of a parameter, in this case, that is on the call frame. Are there any questions? Okay, if there are no questions, I'm just going to write it like this one here. Okay, EAX is actually the address of n at this point. If I add 4 to the address of n, what do I get? The address of n plus 1. That is exactly right. Okay, so this is basically the address of n plus 1. Now it is plus 1 and not plus 4 because n is an integer. Okay. Now at this point, I don't know whether it is an integer or an address, a pointer. If it is an integer, whether it's a 32, whether it's signed or unsigned, that I do not know yet. But the one thing that I do know is n seems to be of 4 bytes because I'm adding 4 to it. Are we still doing okay so far with this? Now, how do I know whether n is actually a 4-byte thing or not? You look at how n is used later on in this code. So when you look at line 27, okay, or line 28 is a very clear sign that n is treated as an integer and is a 32-bit integer. The reason why we know it's a 32-bit integer is the subtraction instruction has an L in it. So that makes it a 32-bit or 32-bit integer. So that is also helpful as well because now you can basically go back here and say that n is a 32-bit integer and it is also a parameter. How can I tell whether something is a parameter as opposed to whether it is a local variable or not? So go ahead.
Oh, it's above return address?
Exactly. Whether it is above or below ODBP or return address. Either way, either one works. Okay, very good. So it's from all of these bits and pieces that I can start to pick up what the various components are and start to document it. So for a question like this, I would do it this way, kind of understand the entire code first before writing the actual code in C or C++. So now we get to line 24. Line 24 is just copying Eax to PTR. And we already know that PTR is a local variable because if you look at line 12 defines PTR, line 11. Line 11 defines PTR to be OEBP minus 4, and OEBP is 0. So that means PTR is something that is 4 bytes below where the frame pointer points to. That makes it a local variable. Okay. So we now go back to here and just kind of comment on it and say PTR is a pointer to a 32-bit integer. And this is a local variable because it is on the other side, it's on the negative side of EBP. But do we have any questions at this point? So it's from kind of looking through the code, looking at how the various constructs are being used that I can start to deduce what is PTR, what is n. The one thing that I cannot figure out right now, and maybe not even ever, is whether n is a 32-bit signed integer or unsigned integer. So that part I cannot tell right now until I can get to a conditional branch, which is actually there somewhere. Then we can actually tell whether it's a signed or unsigned integer. Yep.
Does it matter if it's signed or unsigned?
It is because if the assembly code tells you, has clues to tell you, then the proper C code should be either signed or unsigned. It's because it should be one or the other, but not undetermined.
But it won't change the way it works, will it?
It does change the way it works because if you pass, let's say you, so let's say if you say this, then if I pass you a negative number, the logic of the program may decide, if n is already less than or equal to 0, there's nothing to do. On the other hand, if this is unsigned, and you pass a quote-unquote negative value to it, that becomes a really huge positive value under the unsigned interpretation, and then it will go through a lot of code, a lot of iterations if the loop is saying, if n is greater than 0, do the following. So it does matter, but it depends on the code. For some programs, it may not matter as much. For some other programs, it does matter. But in this case, it does because if you look at how n is used, one place it's actually used is here. Okay, so let's kind of skip around a little bit. Well, actually, let's finish this part first, and then we'll do the other one. So this is basically saying just in C, PTR is the address of n plus 1. Or basically the next integer, the integer next to where n is as a parameter. Okay, So when we get to here, we will try to analyze this code here. The label seems to suggest that this is the beginning of a while loop, and I'm not going to be so tricky to use the conditional statement label when I'm labeling something that is actually a part of a loop. So you don't have to worry about completely misleading labels, saying, oh, this is a loop, but it's actually a conditional statement or vice versa. Okay, so if you see while begin, it's probably just a while loop, the beginning of a while loop. Okay, so that means you know that you're dealing with a while loop here, and the question is, what is the condition of the while loop? So you say, okay, we're trying to figure out what is the condition here at this point. So we somehow save parameter n first. Okay, we're pushing it on the stack. So typically, when you push something on the stack, it is meant to be restored later on, or it is going to serve as a parameter when we call a subroutine. Those two are the main reasons why we're pushing something on the stack. In CISC or CISC, complex instruction set computers, we can have something like this, which is typically not allowed with a RISC architecture. But it does make things a little bit easier to read. All we are doing is to push the value of my local variable n on the stack. And then I subtract 1 from n. Okay, so n gets n minus 1. N is referring to the local variable. And then when I pop, I'm not popping back into n. In other words, I'm not undoing what I just did to n, which is subtracting 1 from n. I'm popping into Eax. So that means Eax is the value of n before the decrement. Okay, so this is the value of n before the decrement operation. Are we doing okay so far with this code? Okay, and then I use the value of n before the decrement to compare to 0, because that's what line 31 is talking about here. Okay, so line 31 is basically saying, okay, on one side we have the value of n, okay, value of n before the decrement. On the other side we have a 0. We're comparing that to 0. We just don't know how we're comparing. Okay, that's a question mark here, because I don't know how it's compared, because the compare instruction itself does not suggest what we're looking for. But the instruction right after that does. Okay, so JNG is now saying if Eax is not greater than 0, using the signed interpretation, we go to end while. Okay, so let's finish this part first. Okay, not greater than is basically less than or equal to. Okay, so now we have the logic to exit the loop, to get out of the loop. Just to be sure that I'm not tricking you or anything like that, you go to the end while label, and truly it is at the end of the while loop. Now how do we know this is actually at the end of the while? Because the unconditional branch is right before that. Okay, so we know that this is the end of the while loop. Okay, so I'm going to comment here and say this is the end of the while loop here. And just kind of put a close curly brace here, just to be sure that we know this is the scope of the body of the loop. Okay, all right. So knowing how we are getting out of the loop, can we tell how we are staying in the loop? It's just the flip side of it, right? Okay, if we're getting out of the loop because n is less than or equal to 0, that means we're staying in the loop as long as n is greater than 0. Is that making any sense? Now it's not really just n, it is the value of n before the decrement. Okay, so that part is kind of important. All right, so once we understand that part, we go here and then we say exit the loop if and only if the value of n before the decrement is less than or equal to 0, because that's exactly what we're observing. This is really just documenting the assembly code itself. But the next line is more important, because now it is relating the code that we're seeing here to a control structure that we know in C++ and in C. So basically it's saying, stay in loop if and only if the value of n before the decrement is greater than 0. Okay? All right. So all of this stuff about talking about n before the decrement, and then but n is actually decremented by this point. I'm just working with a temporary value of n before the decrement, does that correspond to any construct in C and C++ where the side effect is changing the value of a variable, but the value of the expression is the variable before the decrement?
I post decrement greater than 0.
Yep, and actually,
yeah,
yeah, but you get the right concept. It's a post-decrement. So in this case, we can now say, okay, this is just while n minus minus is greater than 0. Okay, is that making any sense? Yep.
Is that any different from having n is greater than 0 and the decrement inside the loop?
It's not exactly the same. Okay, it's not exactly the same because if I do it this way, when we get out of the loop, n gets decremented anyway. If you do it in the loop, then you're missing one decrement when you get out of the loop. So for the purpose of getting out of the loop, it is the same. But if you observe the value of n after the loop, then it's different. Okay. Any other questions? No other questions? Okay. What are we actually doing in the loop? Okay, so I'm going to put an open curly brace here to indicate this is the beginning of the body of the loop. All right, we are seeing some construct that's similar to what we are seeing before. So I'm basically saving PTR on the stack. Okay, on the stack, and then I do something about it. I'm adding 4 to the stack pointer. Not the stack pointer, but PTR as a variable. Okay. We already know that PTR is a pointer to an integer. Is that okay? So the question now is, if PTR is a pointer to an integer, and I'm adding 4 in assembly to the pointer itself, how do I denote this in C and C++? I'll give you a few choices. In C and C++, do I say PTR gets PTR plus 4? Or do I say PTR gets PTR plus 1? That's the question. Plus 1, that is correct. Because in C and C++, when you plus 1 to a pointer, it is type specific. It depends on what is the type that is pointed to by PTR, and the actual address is increased to point to the next thing. In this case, a thing is an integer, and that's why in C and C++, you just have to say plus 1, which is saying, okay, let's move on to the next item. But in assembly, you have to add 4 because each item that PTR points to has 4 bytes. Are we still doing okay so far? So when you look at line 39, it does change my local variable PTR. PTR is changed on line 39, but then on line 40, I restore the value of PTR into Eax. So I'm not undoing what I'm doing on line 39, because now I restore the old value of PTR to Eax. Haven't we seen something like this before? The post decrement, and this is it's a post increment of a pointer. Okay. And what exactly are we doing with the post incremented PTR value? This is a dereference, isn't it? Okay. So we are basically dereferencing the old value of PTR before the auto increment operation, and then we store the dereferenced value, not store, add to sum, and sum is a local variable. Okay, so this is basically just line by line translation here, and now we have to translate it into actual C code. How do we translate this into C code? Let's figure out all the components first, and then we'll try to figure out, okay, how do we group these things together? Okay. Okay, so the components are this. Okay, so we have a PTR++. Okay, we know that because we are incrementing the pointer, but at the same time we want to get the value of PTR before the increment and do something with it. Okay, so we got that one. The other one is the dereference operation. The dereference operation is the instruction on line 41. So we are dereferencing something, which is the result of PTR++. And then the last thing that we are doing is we're adding something to sum. So sum is getting added. Some value is added to sum as a local variable. Is that okay? Does everybody agree that on line 44, 45, and 46, those are the things that we are actually doing here? We just don't know quite how to specify the order of those things. Is that okay? All right. But using the assembly code, we know that the PTR++ is the first thing that we do, right? And then the dereference is the second thing that we do, and then sum plus equal to something, or adding that value to sum, is the last thing that we are doing. So how do we write the code to specify the order? So I think we can pretty much agree that this part is just the way it is, okay? So the next thing is, how do we deal with the dereference in the context of PTR++? That would do it, okay? If you doubt the operator priorities, like if you do not specify the parentheses, there's a question of, okay, are we incrementing the pointer first and then do the dereference, or are we dereference, or are we post-incrementing whatever PTR dereference to? Because there's always that question, unless you know the priority of all the operators, which I cannot even remember most of those. I can remember plus, minus, multiply, and division. That's all I can remember. Okay, so I use parentheses to specify the order whenever possible, because this way there's no ambiguation. Are we doing okay so far with this part? Kind of. Any questions?
Is this being recorded for later?
I think so. The recorder was, I verified that the recorder was on. Yep, it is still going. And it is still recording my voice, so it's not silent. Yeah, this one would not be very helpful if it's silent. Yep, go ahead.
Okay, so when you say pop Eax line 30,
Line 30? Yep.
so what's stored in Eax? Was it
Whatever I push long right before this.
push long? So you push long to push the end.
Yep, that's what I pushed. So the pop is gonna pop that back into Eax. It would be pretty much the same thing as saying, move L, N EBP to Eax, and then, do the subtraction from N. Could be the same thing. Any other questions? But using pop, push and pop, I can delay and I can use Eax between the push and the pop. I can use Eax for other purposes. So that's why sometimes I prefer to use push and pop, because it doesn't, I'm not running up against a risk of, clobbering a register when I still need to use it. Okay. All right. Any other questions? Right. Well, that's the only thing that we are doing in the loop, because then we have the unconditional branch back to the very beginning of the loop. And then after the loop, we only got one thing to do before the standard exit code, and that is copying sum to Eax. And why do you think we are copying sum as my local variable to Eax? What is the role of Eax at the end of a function? The return value. So this is the same thing as just saying return sum in regular C. Right, so I think we have a pretty good idea of what the algorithm is actually doing. So now that we have this part kind of all done, we'll go ahead and let's see what I'll do here. Because I want to kind of keep this around and then use another file to kind of store the cleaned up version of the code. Go ahead.
Did we look at what the
the parameters. But that's the fun part. Let's look at the code first, and then we'll try to kind of reverse back to how it is actually being used. Okay, because we're trying to look at the assembly code and only the assembly code, and then we want to look at how the call is actually doing it. Okay, all right. So let's see if we have missed anything. Okay, let's find out what sum is. Sum is a 32-bit, and we know it is signed because a PTR is a pointer to a signed integer. So it's a 32-bit signed integer, and we know n is 32-bit integer, and it is already, we know it's signed because we use j and g as the conditional branch. And PTR is a pointer to a signed 32-bit integer. It's a local variable. This is also a local variable here. Yep, I think we got most of the things that we need to write the actual C code. So what I'll do is I'm going to kind of move this one to the side and have the comments still visible here, because at this point I don't need to look at the assembly code anymore. I just need to look at the comments. And I'll open a new window. There we go. Over here to look at the actual code. So we'll go to practice and q1.answer.txt. So that's the answer to the whole thing. All right. So the subroutine is called what? Sum n, right? All right. So sum n has a return value of sum, and we know what sum is. We know what the type of sum is. So that kind of implies that the return value or the type of the return value is also an integer, and the name of the subroutine is sum n. We know it has one parameter, which is n, and we'll go for that for now. Okay. Inside we have two local variables. We have PTR as a local variable. We have sum as another local variable. Both of those are signed integers. Or one is a signed integer, the other one is a pointer to a signed integer. Sum is a signed integer, PTR is a pointer to a signed integer. Are we doing okay so far with the C code, the cleaned up C code? It's just a summary of what we have talked about earlier. Okay. So in the other window, now we can kind of scroll down and then figure out, okay, let's see what we are doing here. I already have that line summarized here, so we have a loop. Oh wait, we have the initialization first. So the initialization is right here. Sum gets 0 is the first thing that we do. Sum gets 0, and then the other one is PTR gets the address of n plus 1. Okay, PTR gets the address of n plus 1, and then we have the loop. So with the loop, I'm gonna specify it like this. The loop has a condition of n minus minus is greater than 0, which I copy from here. And if I go down a little bit further, we only have one single statement in the loop, which is sum plus equal to the dereference of PTR plus plus. So now we have sum plus equal to the dereference of PTR plus plus. And then after that, we have another instruction, which is another statement in C, which is just return sum. Is that okay so far? Okay. Well, we only got one problem with this, okay? Because we are now referring to things that are above n, because we keep incrementing the pointer. If you look at the cleanup C code, it is pretty clear what we're dealing with here. This is the address of n, and PTR is the address of n plus 1. So in the call frame, n is my only parameter, so it takes up this space here. And yet the program is using a bunch of values that has addresses higher than that, okay? Which doesn't seem to make a whole lot of sense unless we're dealing with a subroutine that can take a variable number of parameters. Do you guys still remember the discussion of a variable number of parameters for C functions? Okay, so that would be the last part that we have to deal with, is to basically say that it takes a variable number of parameters, which is kind of what find find max n is doing. Okay, so if you remember the homework assignment find max n, that's also what it's doing. Except in that case, you're translating from C to assembly language. In this case, you're doing exactly the opposite of that. Yep.
Would it also have been fine if we used basically passing an array and then using n of 0 for the first one?
If you pass an array, then you cannot. C does not allow you to specify an array of a varying length, of a dynamic length. Okay, I can show you exactly how this is actually used from the caller's perspective. So we'll go ahead and take a look at that. Okay, so this is all done. I'm gonna specify, get out of the editor here. I'm gonna save it. At the end of this class, I will zip up everything and upload it to Moodle, so that you have the video and also the finished product as well. Okay, if you go to the subfolder called Q1, this is actually a project. Okay, and it does specify some and in assembly code. That's the same thing that we have because it's a symlink to it. Main.c is like this. There's a pound if 0 here, and then an end pound if. That's really just for me to comment out from line 4 to line 15. So if you want to run this program not using the assembly code, you can just change this pound if to pound if 1. That will re-enable line 4 all the way up to line 15. And then we can just go ahead and compile the program, let it run, and see what it does. So we'll go ahead and just do that. Okay, gcc-o main.c, and then run the main program. It prints 15. But when you look at how we call sum n, this is how we did it. The 3 is indicating that we have 3 integers to add, and then the 4, 5, and 6 are the numbers that we're actually adding. So in a way, it is different from your homework assignment, because in find max n, we're looking for a particular terminating value, which is the smallest integer value that you can represent using 32-bit. In this case, it is length delimited. The first parameter to n is the number of things that we're looking for. Any questions about this one? No questions? If you guys can do this well, I think a lot of computer security related jobs will need people like you, people who can look at the assembly code and reverse it back into high level code to basically hack programs. You just figure out how something is being done, but in high level code. Are there any questions? No questions? Does anyone like doing this sort of thing? Even if it's outside of the context of a class, like your grade doesn't depend on it?
Depends what we're doing.
Let's say you have a game that you pay money for already, and it's stopping you to do something that you should be able to do.
It's like every day. It's like every day.
So every day? Yeah, but in that case, you'll be treading really kind of dangerous water, because the DMCA can get you. The Digital Millennium Copyright Act says you cannot try to circumvent copyright protection and stuff like that.
Tell them about it. Just don't tell them about it. Don't write it on your Facebook. What you did.
Or you can also, this is also, one of the many techniques that people use, hackers use, in order to figure out vulnerabilities of programs, operating systems, components of drivers and whatnot, because they're looking for a particular pattern of overwriting, possibly overwriting stuff on the stack or some other regions of memory, and being able to look at the assembly code and go back is really helpful. I would show you one more thing, okay? Just related to this, because I do want to show you guys why questions like this is not really just a question, but it is related to something that people do to make a living and to do whatever they need to do. Okay, so if you look at how I compiled main in this case, I did not specify -G, right? If I don't specify -G, that means there's no symbol table. Right, exactly. So when I use GDB on main, I do a list and it says no symbol table is loaded. So it does seem that it's useless at this point. Okay, but on the other hand, if you look at how it is loaded, GDB has a way to disassemble the object code of an executable that it is loaded. Now that by itself can be helpful already, because even though it doesn't show you all the useful label names like sum, sum_n, and stuff like that, it does show you all the instructions, the returns, the JMPs, and so on and so forth. And it's a little bit harder than the homework assignment because you don't have suggestive names where you can kind of think, okay, I think this is this, and this is that. But by looking at how the labels are used and how the jumps are being used, you can still reverse a program and figure out, okay, what is the original code look, what does the high level code look like? So it's, I'm not going to show you exactly how to do that just yet, okay, for a reason. But it is important, okay? This is the kind of skill that people are looking for. Because computer security, at least in my mind, is not just flipping a few switches of an operating system to secure it. It is actually looking into a program and figure out how a program works. And if you're on the attacking side, you try to find a loophole and say, okay, I think I can exploit this here. If you're on the defensive side, then you have to say, okay, we got a problem here, we got to fix this, so it does not become a problem. So this is, I think these are skill sets that are actually going to be useful in the next 10, 20 years. This is going to be a really useful skill set. All right, so here's question number 2. And question number 2 is something that you have also seen already, to be fairly familiar with also at this point. And by the way, the homework assignment is due like 11:55 p.m. today. So that means you still have close to 12 hours to work on it, more than 12 hours to work on it. So it also means whatever I do here may be helpful, to get the homework assignment done. Okay. All right, so let's read the question. Implement this function in assembly code. You may assume the file lstr.inc has the offsets to members defined already, like the ones that we use in the homework assignment. So if you have started on the homework assignment, you should know what I'm talking about. Where lstr node underscore x is defined as a label, and the label is representing the offset in bytes from the beginning of a struct node, from a lstr long string node struct to the beginning of its member x. Now obviously it doesn't have a member x, I'm just using x as a placeholder. lstr node underscore size is defined to be the size of a struct lstr node. Your submission should include the complete content of your lstrrm.s, so you have to include a pound, the dot global and all pound include and stuff like that, ready to be assembled and to be included in the make file. That's a mouthful. That's basically just saying, okay, give me the content of the file that will basically implement this particular function. Are there any questions about what I'm asking, what you're supposed to do with this one? Okay, if there are no questions, we'll go ahead and go over the C code first, and just to make sure that we know what the C code is doing. Once we understand the C code, then we can deal with the assembly code. So the C code is, we have a subroutine called lstrrm for remove. It is for the deletion of a long string. It takes one single parameter. The one single parameter is pptr. It is not a typo. I intentionally used two p's here because it's a pointer to a pointer, as also indicated by the two asterisk symbols here. So it's a pointer to a struct lstr node. And I believe lstr read is the same way. It's a double pointer thing. Okay. Line 16 is basically asking first, is pptr itself null? If it is a null pointer, look, we can go back now. Okay, there's nothing to do. If pptr itself is not null, then we look at what it points to. If what pptr points to is also not null, then we have something to do. because what PPTR points to is a pointer. So we need to make sure that that pointer is not null in order for us to do something. And what we are doing here is we are doing a recursive call first. Okay, this is a recursive call to lstr rm for remove. Then we call a function called free, and then we change whatever PPTR points to a 0, and we're done. There are no loops here because I'm using recursion to do what a loop usually is doing. Are there any questions about the subroutine itself in C? Have we seen anything like this before? We did, right? From the previous class, actually. It's just the previous class that I have explained, something like this. So you can pretty much, plug and modify the template of code that we talked about last time to get this part done. The other parts, I think, are easier. Okay, this is really the most difficult part. Right, so let's go ahead and work on this code. I'm going to split the screen here so that one part shows the C code and the other part will implement the assembly code. So let's go ahead and do q2.uppercase and we'll start with a .global. .global lstrrm is necessary because otherwise the label lstrrm is not going to be seen by the linker, and therefore we cannot link it with the rest of the project. And then we say .text, which is not needed because by default it is in the text segment already. But it's always a good thing to just to double check. Push EBP and pop EBP, and then return here. And then we have a move ESP to EBP. We have to move EBP back to ESP. Usual standard stuff that we have to do for entering a subroutine and exiting a subroutine. So for line 4, 5, 8, and 9, and 10, you can just basically put it in your little cheat sheet and just say that, okay, every subroutine should start with those 3 instructions, every subroutine should end with those 3 instructions. Okay. We don't have any local variables here, so I'm not going to adjust the stack pointer for local variables. So I can now jump on line 16 of the C code and say, okay, how do we implement this here and also that? Okay, because we're basically just checking whether the pointer to a pointer itself is null and whether it points to something that is also null. Okay. Well, since this is a conjunction, that means if PPTR itself is null, I'm getting out. Okay, there's nothing to do. All right, that's fine. So we just have to compare. In this case, one single instruction can do two instructions can do that. I'm comparing 0 because a null pointer is a 0, just a plain 0. So I'm comparing PPTR itself, which is a parameter, to 0, and if it is 0, I'm getting out of here. So go to endIf, and I define endIf right away, just so that I don't forget where I'm supposed to define it. If PPTR itself is not null, it is pointing to a pointer, we want to check whether that pointer, the pointer that is pointed to by PPTR, is also null. So this time I do need to have one indirection, which means I have to move PPTR EBP into a register first, because I can only do indirect with a register. Then I can compare what EAX points to and see if that is a 0. If that is a 0, we also want to go to endIf, because we are basically saying if whatever PPTR points to is null, then it is non-zero. Then it is 0, and it means false. If it is false, then the conjunction becomes false, and then we get out of the conditional statement. Are we doing okay so far with this code? Okay. Then inside the subroutine, this is the nastiest part of the entire thing, which is taking the address of a member of a structure that is pointed to by a pointer, and that pointer itself is pointed to by a parameter. Okay. Yep.
Are we assuming the offsets on here, the PPTR and I guess the P next? Are we assuming we have labels for those?
Nope, we cannot. That's a good point. I would have lost points.
We're grading on a curve against you?
That would be fair, actually.
No. That's a dumb
We
thing
do
to
the
say.
same test we do.
Okay, there we go. So we do have PPTR defined here. All right, and where were we? We were here. Okay. All right, so before we do anything, we'll go ahead and express that nasty expression there in step-by-step instructions, okay? So we are basically take the address of p next of a structure pointed to by a pointer that is pointed to by PPTR. Okay. Now it is kind of important to kind of spell out all these steps. Okay. Now taking the address of is actually the easy thing to do. Okay. When you think about what the compiler has to do, in order to get the value of an expression like this one here, the first thing it has to get to is the address of that thing. In other words, taking the address of something in C and C++ looks like an extra operator to a high-level language programmer. But to the compiler, it is basically saying, you know what, forget that last step to actually get the value. Just give me the address. It's actually a simpler thing to do from that perspective, because you're just getting to the address and you're stopping just one step short of getting the value at the address, which is what you usually do if you don't have the address of operator. So the address of operator is actually easy to deal with. Okay. But when you look at this thing here, taking the address of p next of a structure pointed to by a pointer, that itself is pointed to by PPTR. This is the reverse way, the reverse order of getting things done, because every step depends on the next step. Then it depends on the next step. So the other way to look at this is to say, okay, let's figure out what PPTR is pointing to first. In other words, when we actually work with the code, you have to reverse this order and say, we look at all the dependency and we work out the one thing that everything depends on first, and then we go forward from that point on. So the one thing that we do have immediate access is PPTR. So we put it into EAX first, okay?
Doesn't EAX already have asterisk PPTR?
Yes, it does, but it doesn't hurt to do it again, because you're referring to this part here, right? Because we have to move it into EAX first.
Right.
Yeah, but it doesn't hurt to do it again. If you do it again like this, I cannot take points off. But if you kind of make a mistake somewhere and you forget that you have not put it into EAX first, then you have points deducted. So in situations like this, I just say, okay, let's not depend on what we have done before, because what we did on line 12 is really just to set it up so that we can do the compare on line 13. That was basically the extent of why we copy PPTR into EAX. Now, if you don't do this line here, if you just say, okay, line 21 is not needed, that's fine. I'm not going to take any points off. But I don't remember things from like a few steps earlier, so that's why I always redo it whenever I have doubt about it. Okay. So EAX is now PPTR, and then the next thing we have to do is to say, okay, but we are not interested in PPTR itself. We're interested in what it is pointing to. Okay, so that means we have to use one in direction first. Okay, so now EAX is whatever PPTR points to. Is that okay? So we're working on it one step at a time. Okay, nothing, no big leaps here. Okay, so now we have, so at this point, EAX is a pointer to a structure already. It is not a pointer to a pointer anymore. We just did a dereference to take care of that. So at this point, EAX is a pointer to a structure already. We're not interested in the entire structure. We're only interested in one particular member of the structure. So assuming the offset in bytes from the beginning of the structure to the member that we're interested in is already defined as a label, now we can make use of that label. And that label is going to be lstr node underscore p next. because pnext is the name of the member. So we add that to EAX. So at this point, EAX becomes the address of that part. Yep, go ahead.
You did say up at the top that LSTR pnext is defined as something, or?
Yes.
Oh, okay.
In the question, I think it is already specified.
Okay, I was just wondering how.
Yeah, you may assume the file lstr.inc. Oh, okay, that means I need to do one more thing in the assembly code, which is now include lstr.inc, because it's supposed to be in that file already.
Okay.
All right. So now we have what we need. Okay, let me go back to the C code, because we do want to show exactly where we are at this point. So we got this done already. So what is left to do is to push it on the stack. Push EAX on the stack. Call the very same subroutine that we are in at this point. And when it comes back, we just say, add 4 to ESP, because I don't need it again. Well, we kind of can use it. We'll just get rid of it. Okay, so now we are done with line 18 of the C code. We're moving on to line 19. Line 19 is a little bit easier. Okay, we just move PPTR, EBP to EAX, move. Well, if you want to really save time, you can do that. I mean, that's the same thing as moving indirect EAX to EAX and then do a push EAX. But since the sys instruction set does allow you to use any addressing mode in the operand of a push L, this is the easy, quote-unquote, easy way to do it. And we don't really need to know how free gets its job done. We just need to say, okay, this is what you need, and I'm calling you. And when it comes back, it is time to restore the stack pointer, because those 4 bytes are no longer needed. Well, sort of. And then we are now moving on to line 20. So on line 20, I'm going to move PPTR EBP to EAX, and then move a 0 into where EAX points to. Now this is kind of important, because we are not just we are not putting a 0 into PPTR itself. We're not changing the parameter. We're changing what the parameter is pointing to. So that's why we have to move PPTR into EAX first, and then we move a 0 to where EAX points to. Are there any questions about this code? No questions? All right. And we're done. That is it. Are there any questions? Because I just want you guys to take a look at this again and make sure that you don't have any questions before we move on to number 3. Yep.
Are you able to put the comments on the right side as well?
On the right side of?
Line 26 through 33. You have like 5 lines doing what, 1 line of C code?
Yeah. Well, I can tell you what this is doing. Collectively, by this time we are already finished with all the stuff that we are supposed to do. But the earlier part, I think the commenting of EAX kind of tells you the progress of how we get from one step to another step. And this one is just the call to free, so free PPTR, and this one is PPTR gets 0. Is that okay? All right. Any other questions? No other questions? All right. So let's move on to question number 3. Question number 3 is kind of fun because you have done this already. It's string and compare. But this implementation has well, let's just say, a few things that needs to be fixed. So the first thing you want to do is to find out, okay, give you some test cases, find out which one is going to fail on, okay, and tell me, okay, if string 1 is this and string 2 is that, the exit code is supposed to be this, but it's going to say that, okay? Does everybody understand what I just said? Okay, so give it a test case that this program, it will definitely not give you the right result, okay? So you have to tell me what the right result is supposed to be and what this program is going to tell you. Now, there are other things too. So in this particular program, there are some issues that may not show up due to the address of string 1 and string 2, or the values of extra bytes after the null terminator. Okay, so there may be some additional issues that cannot be consistently shown by specific test cases. But I want you to fix those issues also. Okay, locate those problems and fix those problems as well. So that's basically what it is. I picked a question like this because we all have done the string n compare program. Your version may not look anything like this one, but you know what it's supposed to do. That is the whole point. You know what it's supposed to do. Yep.
How many failing cases would we be expected to show? Just one?
Just one. Yep, just one. But the fix has to work. You have to figure out all the issues with this code and fix all of the issues. Okay. All right. So this is the program. Okay. The usual stuff. I put in the original code, the pseudo C code, in the original program, and let's go ahead and get started. I'm going to split the screen here, just so that we can look at the pseudocode and look at the implementation at the same time. And we'll focus on the first part of the pseudocode first, and then work on this. Okay. So we're going to start on line 52, which is the initialization of Eax. The initialization of Eax, basically seems to imply that Eax is being used as one of the pointers, right? So as I work on this code, I'm going to comment, and figure out, okay, what each register is doing. So in a way, this is kind of like the first one where you have to kind of reverse back to the original code, but at the same time, it also has, something that needs to be fixed. But the upside is we know this code already. We should already know what this program is supposed to do, so that makes it a little bit easier. So we'll just say that Eax is basically doing what P1 is supposed to do, because according to this, P1 points to the beginning of the first string, which is str1. And EBX is the other one. EBX is P2, or the pointer to the second string, and DL is the length for comparison. Okay, so DL is our L. Okay. All right, so are there any questions at this point? No questions? We need to check the length of each thing and see whether it makes sense or not. The address P1 is a 32-bit register. Does that make sense? We are putting the address into a 32-bit register. That's good. So this is good as well. And this is really used as a counter. In this particular case, I'm going to say, well, it's okay. Okay, it's not the best thing to do, but it is okay, because 32 is a number that can be represented using only 8 bits, so it's okay for now. All right, so we now look at line 56. It is a label, okay? L0 is probably a label used later on to come back to this point, because it is a loop after all, so we have to go back to this point, for the repetition. So I'm not going to question that too much. I'm just going to say, is this, while begin? Maybe, we'll check later. Okay, these two instructions combined, lines 57 and 58, is basically saying, is DL 0? If it is 0, let's get out, okay? Because if you locate L2, it is actually at the exit point of the whole program, okay? Because that's basically the end of the entire program, of the loop. So I'm going to say here, is this while end? Seems that way, okay? All right. So this part is basically saying, if L is 0, exit the loop. Seems to be suggesting that. Fine. Let's take a look at these 3 instructions. line 61, 62, and 63 is basically comparing what EBX points to against what EAX is pointing to, and if they are not the same, then we're getting out. We're going to label L1, which is corresponding to this part of the original code. Okay, that's okay. Okay, we can exit right away and then determine what to do. So this is basically saying if whatever P1 points to does not equal to whatever P2 points to, go to L1, and then we'll check out where L1 is. And L1 is down here. Okay, and it is after the JMP to L1. So this is going to go back to while begin. Okay, so that's the end of the loop. So L1 is actually after the loop. Okay, that's fine. So this part is okay. Now we are moving on to the last part of the condition. Is P1 pointing to a null character? Okay. So we are saying, if P1 points to a null character, go to L1. That's okay too. We got that part. Okay, that seems okay. Now we're in line 68, 69, and 70. This one is adding 1 to AL. Okay. What is registered EAX? Yep, go ahead.
Where are you comparing bytes?
Huh?
With the line 65 and line 65?
Line 65 comparing a byte is correct because we are comparing what P1 points to a 0. And what is the type that P1 points to? It's a char pointer, right? So if P1 is a char pointer, we are comparing a byte because we're comparing what it points to. Yeah, so it is correct. Okay, so we have add byte 1 to AL here. What are we using EAX for? A pointer, which is P1, okay? And when we add 1 to a pointer, do we add 1 only to the least significant A bit? It will work most of the time, but when you're adding 1 to blah 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 FF, then the rollover will not work correctly. Is everybody understanding the issue here? This will work like 255 times out of 256. This will work okay, but 1 out of 256 times is not going to work, because when it needs to roll over or have a carry to bit 8 of a 32-bit pointer, then it's not going to work because it's not changing the most significant 24 bits of a pointer. So this is a nasty problem because the program that looks like this will work for the most part. It will work sometimes, most of the time. But when it does have to roll over to the next page, the next 256 byte page, then it will fail, because it will just roll over back to the first byte of the original 256 byte page. And the symptom is going to be very nasty because it seems like it's working for the most part, but occasionally it will not work.
So you have the same issue if you had add W.
Correct.
To AX.
Yes, because in that case it will fail 1 out of 64,000 times. 65,336 times. So 1 out of approximately 65,000 times is not going to be right. And those are really nasty issues because it doesn't show up all the time. So this one needs to be fixed. Okay. So for something that needs to be fixed, I'm just going to comment the original code and say we need to use add long and not add byte here. Okay. Because even though EAX is a pointer to a byte, the pointer itself is a 32-bit thing. It is not an 8-bit thing. And the same issue here. Okay, so add long $1 to EBX, or I should probably do it like this. Okay, should be that. The reason why I'm doing this is because we are supposed to find out issues with this program and figure out the test case where it's not going to work. Okay, subtracting 1 from DL is okay because it is only up to 32, and 8-bit is enough to represent up to 32. So that part we are okay with. All right, this is after the loop. L1 is a label that is corresponding to line 45 in the pseudocode here. So now we need to figure out what we are supposed to do in assembly. We are comparing EAX to CL. What is in CL? Well, we can go back and see, how CL is being used. So assume, because nothing else is touching it, so CL still has the same thing from before, which is what P2 points to. Is that okay? Because in this instruction here, we're moving what P2 points to into CL, so CL is basically whatever P2 points to. So when we get to L1, we should comment here and say, CL is whatever P2 points to, and EAX is whatever P1 points to. So here we have to kind of determine what L2 is really talking about. L2 is basically saying, if P1, whatever P1 points to, is the same as whatever P2 points to, go to L2. Okay, so L2 is corresponding to the case where the two strings are the same. Okay, so this is actually not while and this is actually what to do when the two strings are the same. Okay. Now here we have an issue. This is part of the this is where the problem is. JZ doesn't really matter, whether you put CL first as the first operand or the second operand, because to check for equality, you can flip the two sides and it will give you the same result. But when we're dealing with JA, above, below, greater than, less than, that sort of thing, it's not symmetric anymore. So this instruction here is really saying if and only if whatever P1 points to is greater than whatever P2 points to, because you have to read the operand in a reverse way, go to L3. That's what it's saying. So what is L3 really doing? L3 is putting a -1 into EBX, which is the wrong value to put into EBX. Because the instruction is saying, okay, let me switch to the top part here. Because according to the instruction, I want EBX to be a 1 when str1 string 1 is greater than string 2. So it's doing exactly the opposite. Okay. Is that okay? Does everybody kind of see where the problem is? Because in this case, if we're saying, if whatever P1 points to is greater than whatever P2 points to, we go to L3. But when you go to label L3, it is putting a -1 into EBX, which is opposite to what we want. Which also means the other label is also going to do the opposite, because it's going to L4, where L4 is putting a 1 into EBX. So there are two ways to fix this problem. You can change the label that they're going to. You can also change the values that they're putting into EBX at the label. So I'm going to fix it this way. I'm going to say this one should be move L $-1 to EBX, whereas the other one is supposed to be, should be move L $1 into EBX. All right, so knowing this, okay, how do we construct a test case to make this program do something that it's not supposed to? Don't give it a long string, because if you give it a very long string, you might wrap around that 256 byte thing, and it will give you some result that is unexpected, that cannot be predicted.
Any strings that aren't equal are going to return the wrong value.
Yes. So you have to make it as short as possible, right? Just to make sure that you don't accidentally hit that end of 256 byte page thing. How about a null string versus a string that has just A in it? Okay, so we'll give it a try. Okay. So at this point, we have just commented everything in the program. We haven't fixed anything yet, because I commented out the changes that I was making. So let's go ahead and actually run this program to make sure that we can report a test case where the program is not going to give us the right result. So we do as-2steps-o q3.o q3.s LD dash Q3, Q3. I think they're probably fixing something on the roof. Not open file Q3 is a directory. Oh, okay, Q3 exit. Okay, there we go. So we're going to run gdb Q3x, and we'll put a breakpoint where we are starting. So we put a breakpoint on line 28. Make breakpoint pending on future shared library code. That is odd. Reassemble, and then we link Q3.0 to Q3x, gdb Q3x. List. Okay, well, that would always work. Okay, that's work. Run the program. We are now at the no op instruction. And let's go ahead and fix this program. The dot fill will automatically fill out the strings with all the no characters already, so that part is okay. We'll just have to put a non-no to the first character of one of those strings, and that can be done by set str1 equals to the ASCII code of lowercase a, which is 61 in hexadecimal, and then we'll double check, make sure that is the case. So x/3bc, the address of str1, and that's just an A with a no terminator. That's good. And str2 is all no, so that's good too. Okay. And then we'll put a breakpoint at the end of the program. So I'm not going to rely on the program reporting back to me what is the return code. I'm just going to put a breakpoint where that's supposed to be at. So we'll just keep that is really odd. Never seen that before. We'll put it at label L5, which is the same thing as line 104. It's just another way of expressing that. Continue the execution of the program. Print what is in EBX, and it is a -1. It is supposed to be a 1 because a string that has a single letter A is supposed to be greater than a empty string. So that completes the first part, and if you look at the suggested changes, it will fix the program, and that will be the second part of the program. All right, just in time. Over by 2 minutes. Pretty close. So are there any questions about this? If there are any questions, I'll be in the lab, so we can talk about it in the lab too. And then you can work on your homework assignment if you're still working on it. You still have about 12 hours to work on it, a little more than 12 hours. So let's go get the last homework assignment done. I like question number 3 because I don't have to do anything.